Welcome friends to my YouTube channel Sommo Physics. Yesterday I have started the second chapter of thermodynamics, that is the Carnot engine and second law, and there I told that what is the heat engine and what is Carnot engine and its basic features. Now I also discuss about Carnot cycle. Now in today's lecture I shall going to discuss about the efficiency of a Carnot cycle. Okay, so let's start. Now consider that PV diagram. Okay, so just draw the PV diagram. Okay, now yesterday I told that here two successive expansions and compressions is done, that is along AB isothermal expansion, along BC adiabatic expansion. Okay, along CD isothermal compression, along DA adiabatic compression. Now here the working substance we take is usually a ideal gas as working substance. Okay, here we take ideal gas as working substance. Now this point, that is this point represents the initial state of the gas, that is P1 V1 T1. Okay, this point A represents the initial state of the working substance. So its temperature at A is T1. That means this point is attached to source. That means if its temperature is T1, then source temperature is also T1. Okay, source temperature is also T1. Since this point is attached with the source, at point A source temperature is equal to the temperature of the working substance. So starting from the point A, the gas expands isothermally until it reaches to B. So if you take the point B, then pressure and volume changes, but since the expansion is isothermal, the temperature remains same. Okay, now we all know that in isothermal process temperature remains constant and we consider ideal gas. So in case of an ideal gas, okay, internal energy is also a function of temperature only, that we learn in first law for ideal gas. So if temperature remains constant, internal energy remains constant. So here the change in internal energy is 0. That means what we get? So that means work done by the gas, this must be equal to heat absorbed from source. Heat absorbed from source. Okay, so work done by the gas, this must be equal to heat absorbed from the source. Okay, so if W1 is the work done by the gas, then this must be equal to Q1, where Q1 is the amount of heat absorbed from source, and that we can write as integration over V1 to V2 PdV. Okay, because the initial volume is V1 and at B point the volume remains V2. Now we consider ideal gas, so we can use the ideal gas equation, that is PV equal to RT. But since the temperature at this point is at T1, we can replace it by T1. So what will be my P? My P will be RT1 by V, that means RT1 dV by V. So we can write RT1 ln V2 by V1. So this is the expression of W1, and we all know that work done is equal to the area of the Carnot cycle. That means ABBA. That means area under the curve ABBA. Okay, So this is the first step. Now let us move to the second step, that is along adiabatic expansion. Okay, so adiabatic expansion. Okay, now starting from the point B, the gas expands adiabatically until it reaches to C. Okay, starting from the point B, the gas expands adiabatically until it reaches to C. Okay, until it reaches to C. So at B, the pressure is P2, volume is V2, and temperature is T1. At C, pressure, volume, everything changes and temperature also drops down, because we all know in adiabatic expansion temperature of the gas falls down. Why? Because in adiabatic process we all know that there is no exchange of heat between system and surroundings. That means dq is 0. Okay, so from which we first law we can write dw equals to minus du. That means work is performed by gas can perform work without the expenditure of its own internal energy. Work can only be done at the expense of own internal energy of the gas. That's why internal energy decreases and the corresponding temperature decreases. Okay, so in this case no heat enters or leaves the system and work can only be done at the expense of own internal energy. For this reason internal energy and temperature falls down. So if W2 is the amount of work done, so what will be the expression? That is volume V2 to V3 PdV. And since the process is adiabatic, we can use PV to the power gamma equal to constant. Remind it. In adiabatic process, we use this relation. So we can put K into V to the power minus gamma dV. So what will be the result? V to the power minus gamma plus 1 by minus gamma plus 1. V2 to V3. So if you rearrange it, you can write K by gamma minus 1. So this becomes in the, so V2 to the power 1 minus gamma minus V3 to the power 1 minus gamma. So when you multiply K with this term, then you substitute P2 V2 to the power gamma instead of K. Okay, and when you multiply K with this term, you substitute P3 V3 to the power gamma. Okay, for simplification. So what we get? We get P2 V2 minus P3 V3 by gamma minus 1. And what is P2 V2? That is R into T1. We can write P2 V2 as R into T1 and P3 V3 R into T2. That is at C point temperature will be T2. So this is what this represents, this area BCCB. Okay, this represents the area BCCB. Okay, so this is the two expansions that we calculated. Okay, now let us move to the compressions. Okay, let us move to compressions. First, the third step you can do, the gas is a compressed isothermally. Okay, the gas is compressed isothermally. তো এই আর কি ব্যাপার। ও সরি, in third step we the gas is compressed isothermally. Compressed isothermally. Okay, now one thing you have to notice here, whenever we consider that work is done by the gas, we will take it positive. Okay, we assume that under expansions the gas performs work, so we take it positive, and whenever we consider compression, that is work is performed on the gas, we will take it negative. Okay, so in expansion the gas performs work, we will take it positive, and in compression the work is performed on the gas or on the system, so we will take it minus. Okay, remember this thing. So now remember, this is connected to sink. Okay, that means along this line isothermal compression will takes place, and what will be the work done during this process if on the gas, that is this must be equal to Q2. That is, in isothermal compression the work done on the gas, that must be equal to heat rejected to the sink, because this is a source and this is sink. Okay, now you can check it. So work is done on the gas. Okay, so work is done on the gas. So what will be its expression? We give a minus sign because work is done on the gas. This is simply V3 to V4 PdV, and we can change the limit V4 to V3 and we put PV equal to RT, but here the temperature at every point on this line is T2, so substitute T2, so that is RT2 dV upon V. So this will be R into T2 ln V3 by V4. Okay, so this represents this area under CDDC. ঠিক আছে, area under the curve CDDC. Okay, just remember this. Now the last step we have to do is the adiabatic compression. Okay, adiabatic compression, and we see that in adiabatic expansion the temperature falls down. Similarly on adiabatic compression the temperature rises, and finally the gas reaches to the initial state. Okay, finally the gas reaches to the initial state. Now in this case also work is done on the gas, and the limit will be minus V4 to V1 P dV. So it will be V1 to V4. Here we put P into V to the power gamma equal to constant, that means this. So if you simplify it, you will get the same result as the result obtained in case of a adiabatic expansion, and which will nothing but R by gamma minus 1 T1 minus T2, and this is simply the area under DAAD. Okay, now we have obtained the work done and heat energy absorbed in 4 cycles individually. Now what will be the total amount of work done during the entire cycle? If we call it W, then expansions are added, we give plus sign to expansions and minus signs to compression. So if you substitute that value, you will get RT1 ln V2 by V1 minus RT2 ln V3 by V4. So Q1 minus Q2. There you see that W equals to Q1 minus Q2. That means the heat absorbed from the source will not be completely delivered to sink. A part of it is used in work, while the remaining part is rejected to sink. Okay, so this is the expression, very important expression. Okay, now efficiency of a engine is defined, Carnot heat engine, as the total amount of work done in the full cycle by heat absorbed from source. So what will be the result? Q1 minus Q2 by Q1. So that means 1 minus Q2 upon Q1. Okay, this is the efficiency of a heat engine. Okay, now we can write it in terms of temperature also. Okay, how? These 2 points lie on same adiabatic curve, and we derived the relation, adiabatic relations for a perfect gas in our first chapter. Here we use TV relation, and what would be the TV relation? T into V to the power gamma minus 1 equal to constant, say K. That means use this relation for the points A and D. So what you will get? T1 V1 to the power gamma minus 1 equal to T2 V4 to the power gamma minus 1. And if you use this for point B and C, what you get? T1 V2 to the power gamma minus 1, this is equal to T2 V3 to the power gamma minus 1. Okay, so if you divide these two relations, you will get V2 by V1, this is equal to V3 by V4. This is known as volume expansion ratio. Okay, this is known as volume expansion ratio. Okay, so let us try to find out the efficiency in terms of temperature. That will be more accurate. Okay, because our main aim is to show that efficiency is independent of working substance. Okay, so if you put eta, this is equal to 1 minus q2 by q1, and what is q2? RT2 ln V3 by V4, and what is q1? RT1 ln V2 upon V1. RR cancels, so V3 by V4 we get R, and also V2 by V1 we get R. So this also cancels, so this is the result. Thus, this expression clearly indicates that efficiency of the Carnot engine solely depends upon source and sink temperature, and it is independent of the nature of the working substance. Okay, so eta only depends upon source and sink temperature. Okay, so this is what I did today. Now in our next class I will discuss about few other issues regarding heat engine. Okay, so dear guys, if you don't subscribe my channel, then kindly subscribe it to get latest videos on physics. Thank you.